Hi everybody, today I want to talk about Fermat's principle, all right? And the principle states that the path taken by a ray traveling between 2 points is the path that can be traveled in the least amount of time. All right, so if I have point P and point Q, I've given you 3 paths here. The path that the light is going to travel is the one that takes the least amount of time out of all of those. Not an obvious statement. What we're going to show today is that you may have learned Snell's law in your physics class. We're going to show that that path that the light takes is actually the one that corresponds to the world famous Snell's law. All right, to illustrate this principle, what I'm first going to do is I'm going to consider a simple numerical example. Okay, so part 1 of the video, we're going to plug in some numbers, calculate the time for different paths, and show that there is one that's going to be the shortest. Okay, in this part 2, what I'm going to do is a more rigorous calculus approach. Once I have an expression for the time it takes to go from one point to another, if I want to find the shortest time, I can minimize this function in order to solve it. And what we're going to show is, if I do the calculus correctly, that this is going to lead to Snell's law. So that's all done in part 2. All right, the last part of the video is basically another calculus approach, but it's a little bit more of an elegant, more advanced problem-solving method that involves, if you're trying to find an extremum of a function, which in our case is going to be the time taken, you can use a solution to the Euler-Lagrange equation. And I'm going to show you how to do that. How do you set up the function and then plug it into Euler-Lagrange in order to, again, obtain Snell's law. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. So we're going to start off by considering an example here with some numbers. I'm going to assume that my starting point for the light here is at point P. It has a coordinate of -10, +10. And my origin here is right here in the center of the figure. The top medium has an index of refraction of 1.3. All right, the bottom one here has a larger index of 1.8, and I want the end point of the light to go to this point Q, which in this case here for this specific example is going to be at a coordinate of 10 - 10. Okay, now there are various paths that it can take. One thing we have to know is, now although the speed of light is 3 × 10⁸ meters per second. For this example here, what we're going to do is just to simplify the numbers a little bit. I'm just going to omit that 10⁸. So I'm just going to set the speed of light equals to 3 meters per second. Okay, just it'll keep the numbers kind of easier to work with. Now, the speed in each medium, okay, that is given simply by the speed of light in a vacuum divided by the index of refraction. In this case, it would be n1. So I can get a number for that. The speed in medium 2 is going to be, again, speed of light in a vacuum, my 3 value, divided by the index n2. Okay, so I know the speed in each media. Okay, now the next thing I want to consider are, let me show you 3 different paths that start at point P and end at point Q. All right, here's 3 different paths. The path labeled 1 goes right through the center. The path labeled 2 spends more, right? The distance, at least in medium 1, is longer and has a shorter distance, at least in medium 2. Okay, and look at path 3. Path 3, the distance that it would propagate in medium 1 is short, however, larger distance in medium 2. All right, what we want to do now is we want to get an expression to calculate how much time it takes to go from point P to point Q, for example, for any one of these different paths. Okay, and here I'm only showing you 3. Clearly, you can choose any path here that intersects this line here between the 2 media. So let's get an expression for the total time, okay, of propagation from going point P to point Q. All right, let's calculate the total time it takes to go from point P to point Q along this path number 2 here. Now, I've labeled some of these points here. I've given the coordinates for P, Px, and Py. I've labeled the intersection here of the point between the 2 media here as x, 0, and then also the Q coordinates. So if you're looking to calculate time, so time will be broken down into two different calculations, right? It's going to be the time it takes to go from point P to the red point over here. So that I'm going to call time T1. And then to that, we have to add how much time does it take to go from this red point all the way to the green point. I'm going to call that time T2. So the time T1 is going to be, well, what is this distance over here? So you can call this distance, for example, D1. I can call this distance D2. So the time is simply that distance D1 divided by, well, how fast is light propagating in this media? For time T2, it's going to be that distance D2 divided by the speed V2. Now again, using our definition of the speed, we can introduce the speed of light and the index of refraction here. So here we have c divided by n1. And here we would have d2 divided by c divided by n2. Now you can bring the index to the front. That kind of cleans it up a little bit. n1d divided by the speed. And here we'd have n2d2 divided by the speed of light. Okay, add the 1 over here. Now, how can I write this distance d1? The best thing to do, I think, is just to introduce kind of these other distances and then use Pythagorean theorem to write this out. So if I write this out as d1x, d1x, you should see you can write it out as x minus px, right? If this is the coordinate x, that it will be this total distance here. For the vertical distance of this triangle, this one's easier, right? This I can call it d1y, and this here is simply py. Okay, well that's easy to do. Now d1, keep in mind, d1 you can simply write using Pythagorean here as d1x squared plus d1y squared. Okay, now we can do something similar here for the bottom path. Let me do it in a different color. So here I can define this vertical distance for that triangle. This one here is also easy. This is simply qy. All right, and this is the distance d2y. And then I also have this horizontal distance. This horizontal distance, you can call it d2x. Now this one, be also a little bit careful. This should be defined as qx minus x. All right, so now again, you can define d2 in terms of square root and sum the squares of each of those distances. So let's put them all now together in order to get the time t1. So the time t1, I still have that index of refraction. I have that over the speed of light. And now d1, I'm simply going to write it in terms of a square root. Now there's going to be two terms here. There's the d1x squared, which I write as x minus that starting point position squared, and then plus that vertical distance squared. That vertical distance, I just write it in terms of the coordinate, and that's it. That's the time t1. How about the time t2? Again, it looks something similar here. You have the index, you have the speed. You're going to have a large square root, and that term looks something like this. This is qx minus x squared, and then plus qy squared. All right, so that is the time for each of these individual, the time it takes for each of these individual paths, but what we want actually is the total time, right? So the total time, then you have to actually add both of those, right? It's going to be t1 plus t2. That's the total time it takes to go from point P to point Q. So simply rewrite those expressions here, and we get one final expression, and that expression is actually only in terms of one variable, right? Because px, py, those are constant for this problem. And the only variable is going to be x. Where is this intersection point here? So let me just be careful, make sure I transcribe this correctly here. Qx minus x squared, and then plus qy. All right, now what I want to do is we're going to use this expression, again, with all the variables that I've given you here. So remember, all these are constants, that's fine, right? This is 10, that's 10. So it's very easy. I know all the index, I know the speed, I'm going to use 3 for that. And now I can substitute the values of x for the 3 different paths that I showed you in the previous slide. All right, we can calculate a total time for those 3 paths. So let's go do that for in the next slide. All right, to help me with my calculation, what I'm going to do is just use a little bit of Python code. If you don't know Python, it's okay. It's a very, very simple little bit of code here that I'm doing. I basically just want to calculate this expression down here at the bottom that we just obtained for any value of x. So I'm going to feed it some value of x, and my function, I'm going to call it Fermat time. Okay, I've defined the constants over here inside this function. So I have the speed, I have the indices, 1.3 and 1.8. Now the first thing I do is I calculate the speeds v1 and v2 over here. Next thing I also do is I define the coordinates, right? What are the coordinates p and q? Okay, those are given down here in the figure. And again, these are constant for this problem. And at the end, I eventually want to calculate this expression for time. So I need these square roots here, and I've defined all these distances, d1x, d1y, and so forth. You can see it's exactly like we just did in the calculation. And at the end, this function is simply going to return this total time that it takes, right? Because I'm adding t1 to t2 to get the total time. So let's go back to those three paths and see what we get. All right, I went and I substituted the values of x for these three paths. So for path number 1, the x value is 0. Okay, if I do Fermat time, substitute the 0 in here, I get a time of 14.61. If I do x equals to 5 for path number 2, you see I get a time of 14.52. It's a little bit smaller than the first path. And if I do the red path, path number 3 over here, if I substitute the x value, which is -7, well, what you get in that case is a much larger time. In this case, it's 16.36. Okay, so one thing you notice is that the amount of time that it takes, look at path number 1. Path number 1 is actually the shortest path between both of those points. However, it is not the shortest amount of time. Okay, and it's not because there are different speeds. Okay, if you think about these speeds v1 and v2, v1 is faster, so you can spend a little bit more time over here in this top medium because light is propagating faster in this medium. Okay, it wants to spend a shorter amount of time in medium 2, okay, because its speed is slower because the index is higher. Okay. All right, we just calculated the total time for 3 specific paths, but what I have here is my total time really in terms of that variable x. So I could do it for any value of x, for example, between -10 and 10. And if I do that, I get this blue line. So I'm showing the total time as a function of that x value. The 3 points that I've already considered here are shown also on this plot. For example, path 1 has an x value of 0. We got that time over here. Path 3 had the x value of -7. Path 2, again, had the x value of 5. But one thing that jumps out at you from this figure is that that amount of time has this minimum value right here. Right? Look at this. There's some x value, right? There's an x value here, which I calculated numerically, and that x value is approximately 3.0142 for these numbers that I've considered in this problem. That gave me a minimum time, I'll call it T minimum, for the total time of approximately 14.431. Again, it's a little bit less than path 2 and path 1, and that x value is right about here. So now you draw a straight line that goes through here, and then it goes down here all the way to point P. So I wish my line was a little bit straighter here. But you see that there's some value of x that gives you a minimum, okay? And that is the real key to this understanding Fermat's principle. Out of all the paths that are possible, there is only one that gives you a minimum amount of time to go from point P to point Q. What you can do now is what we're going to do is we're going to use some calculus in order to find what is the minimum time. And all you have to do is you have to differentiate this function here with respect to x and find where that minimum value happens. And we're going to see that that minimum value happens when Snell's law is satisfied. Okay, so that'll be the next part of the video. All right, so what we want to do here, this is my expression for t total, and my goal now is to minimize this with respect to x, right? Because x can take on a whole series of values. Well, from a calculus standpoint, when we want to minimize something, it means we want to differentiate it with respect to x and set it equal to 0. This is going to find an extremum, and we've seen from the graph that in this case it will correspond to a minimum value of time. So all you have to do then is take this expression, which has x in two spots, and differentiate it with respect to x. Now you got to use the chain rule here because the x appears under the square root. But if you're careful with that, you should get an expression that looks like this. Okay, now this looks rather messy here. There are constant terms, and what we're doing here is we're setting this derivative equal to 0. So that simplifies our lives quite a bit. Now I'm just going to rewrite this and put some of these terms that have a minus 1/2 exponents here, which come from differentiating this square root term. All right, you can go ahead and rewrite this a little bit more neatly by bringing some of these square root terms here to the denominator. The next step you do is we can cancel out some constant terms and those factors of 2 that appear in both the numerator and the denominator. They cancel the constants because, again, all this is equal to c. Therefore, if you factor it out, it doesn't affect the final answer because the constants appear in all the terms. All right, the last step, well, maybe bring one of these. You see I have a negative sign left over here. Maybe bring one of these terms, everything here in the blue bracket, bring it to the other side. And what you get now is a simpler looking expression. Now it looks kind of complicated here because it has some differences here of x and px and qx and x and all these things. However, you have to remember how these things were defined from the onset of the problem. Right? If you remember how they were defined from the onset of the problem, this simplifies very, very nicely. Okay, first of all, the x minus px, we had simply defined that as d1x. And this whole term in the denominator here on the left-hand side, this was by definition the distance d1. And it was a similar expression for the right-hand side of this expression, except it involved side number 2, right? Let me go show you if you don't remember that, right? This was our original definition of all of these different lengths, okay? So if you simplify that expression here, again, what we've done now is if we minimize the time, okay, and that's what we're doing by differentiating with respect to x, you get to this expression right here. Now, what we're going to do is we're going to simplify this one step further, okay? The first thing I'm going to do is, well, let's look at those distances. d1x is this distance down here. Well, I can actually move that, right? It has to be the same distance as this one. This is also d1x. What I'm going to do now is I'm going to introduce an angle. The angle is going to be relative to this vertical dashed line, okay, which is perpendicular to the media here intersecting, okay? Now, if you see this, if I use a trigonometric function, for example, sine theta, and I call this theta 1 here, sine theta is the opposite over the hypotenuse. That is exactly what this term is, right? Which means you can write this side here as n1 sine theta 1. Now this should look familiar to you. How about the other side? Well, again, the other side involves this fraction, d2x divided by d2. d2x is this side. Again, if you define this angle here with respect to the vertical, or with respect to, say the vertical direction, look what you have here. You're going to have this side has to be equal to n2, that index of refraction. That hasn't changed. And now this is d2x divided by d2 is the definition of sine theta 2. And look what we've done, right? It's quite a miracle. By minimizing the time, what do we get to? We get to this expression here. And it tells us this is effectively the statement of Snell's law. Okay, so the light traveling from point P to point Q obeys Snell's law, and it's a result of, guess what? By minimizing the time it takes to go from point P to point Q. Quite a remarkable result that comes out of Pascal's principle. We're able to prove this Snell's law relationship, okay? All right, to start this Euler-Lagrange equation method, what I'm first going to highlight again is that we have medium 1 on top of medium 2 the way it is here. My coordinate system is defined here as y is in the vertical direction. If they have different indices of refraction like I have here, it means that the speed will be different in the top half versus the bottom half. All right, in terms of an equation, it simply means we can write the velocity is then going to be a function of this vertical distance. For example, if y is greater or equal to 0, I'm going to have one value of v. And if y is less than 0, it's going to be equal to v2, right? Because of the different index of refractions that we have. Now, the next step is we're going to consider a small element of length right here. Now, if I zoom in on that and I call that total length of that element ds, here I break it down, right? It has a horizontal distance dx and a vertical distance dy. All right, the next thing I could do is I can use Pythagorean in order to write that little element of length ds as being square root of the sums of the squares of the length of the sides of this triangle. What I want to do now is I want to factor out a dx, okay? And if I do that, this is what the equation looks like, okay? This is pretty straightforward mathematical manipulation. All right, now the next thing I want to do is I'm going to introduce a definition. I want to just simplify the notation here a little bit. So what I'm going to do is I'm going to call y prime as being dy over dx. What that allows me to do is just write a more compact form for this length of this element ds as this final expression right here. Okay, so I have that element of ds equals to the square root of 1 plus y prime squared multiplied by dx. Okay, this will be the length that I'm going to use. All right, the next step now, step 2, is to calculate the time to travel from point P all the way to point Q down here. Well, remember that the time is simply the distance divided by the speed, right? So if I consider the amount of time that it takes to just travel one small segment over here, well, then you could simply write that as ds, that's the distance, divided by the speed, and I'll write it as v being a function of y here. All right, nothing too complicated. Next thing I do is I'm just going to substitute my expression for that length ds. Okay, so that's all I'm doing. There's the length ds that we had, and I'm still dividing by this speed function here, which is a function of y. All right. The next step you want to do now is, well, we don't want to calculate just a little bit of time. What you're really interested in is what is the total time now to go from P to Q. Okay, and to get the total time, what that means is you really want to integrate all of these small elements of time dt. Okay, so I integrate all of these elements dt. Now we substitute the expression we have for dt in this integral, right? And this is what we have now. Okay, so we're integrating over dx. We're integrating starting at px going all the way to qx, and here is the function here that appears in this integral. All right, now this here is going to be our starting point for the Euler-Lagrange equation. All right, so we start with our total time expression that we have, and what I'm going to do now is I'm going to define something called the Lagrangian. Okay, Lagrangian is basically grouping all the terms together other than the dx. Okay, I'm going to call this a function f, and if I write it out, we notice here that this function f depends on y through this velocity term or through the speed of light in that medium, and it depends on y prime, okay, through the square root term right here. So we notice that this here is actually independent of x, right? It doesn't depend on x explicitly. It doesn't appear x anywhere in this expression right here. That means if you were going to take a partial derivative of f with respect to x, now note this is a partial derivative, okay? It's not the full derivative with respect to x. But if you take the partial, you would get 0 on that side, okay? Now, step 3 now is basically applying the Euler-Lagrange equation. And it basically says if we're looking for an extremum of this value t, which we are, right, we must solve the Euler-Lagrange equation. What we're interested in is finding an extremum. In our case, we're looking for a minimum of time it takes to go from point P to point Q. So that is an extremum of t. And now it basically says, well, that function f must satisfy this Euler-Lagrange equation if we're trying to find an extremum of t. And this here is the Euler-Lagrange equation. All right, it says the partial of f with respect to y minus d dx of the partial of f with respect to y prime equals to 0. All right, now what makes this equation rather complicated for this case is this first term right here, right? The first term, we have a partial of f with respect to y. Well, that term is not 0 for this problem because we have that the speed here depends on that variable y, okay? So in a lot of problems, sometimes this first term vanishes or set equal to 0. It does not in this case, which makes it a little bit complicated. So we're going to have to circumvent this and introduce a second equation that's going to help us obtain a solution. All right, so we have our Euler-Lagrange equation. I'm going to label that equation 1, and now I need a way to deal with this df over dy. Now I'm going to do some math here, and it's going to seem like, why am I doing this? But you'll see why in a minute, okay? We need a way to deal with this first term over here, okay? So how am I going to deal with that? Well, I'm actually going to take the full derivative of that function with respect to x. Let's just write down an expression and see if we can simplify and introduce a term that's similar to this. So if I write this full derivative with respect to x, again, this is just the definition because my function f, my Lagrangian, depends on y and y prime. So if you write the full derivative, you're going to have 3 terms. However, as I've written right here in the green part, the partial of f with respect to x, look it doesn't depend on x. So that simplifies this first term, so that's kind of nice. Now, what you can do is introduce some similar definitions to what we did previously. For example, if I call y prime dy over dx, and if I call y prime prime, I call it as the derivative of y prime with respect to x. Okay, so that's just going to simplify the notation here for both of those terms here on the right-hand side of my full derivative. So if I do that, this is what it boils down to. The full derivative of my Lagrangian with respect to x is equal to the sum of both of those terms. Now the reason I want to do this, well, look at this first term. This first term looks exactly like the term in the Lagrangian right here. All right, so what I'm basically going to do then is I'm going to label this equation 2, and we're going to do some math in order to obtain another expression that is satisfied by my Lagrangian. Not only the Euler-Lagrange equation, but when we combine both equations 1 and 2, we can get to a second equation that is satisfied by my function f, and that's going to allow me to solve this problem. All right, so this is what we have, our 2 equations right here. The first thing I want to do now is we're going to have to combine them somehow, and the way I've decided to do this was see this df over dy. It appears in the second equation, so I'm going to use the Euler-Lagrange equation in order to substitute this term into the second equation. Okay, so that means you have to bring this term to the other side. And if you do that now, this is what it looks like now. So I've simply replaced that first term in equation 2 by using the Euler-Lagrange equation. Okay, so this is looking kind of messy at this point, right? What we're going to do now is we're going to try to simplify the term here on the right-hand side. Now, it's not obvious by looking at it. The mathematical step to do this is you have to recall the chain rule. And imagine I'm going to take the full derivative with respect to x of this function here, y prime, multiplied by df over dy prime, right? So what you would do if you were going to apply the chain rule for this, well, it would look something like this, right? You'd take the derivative of the first term with respect to x, you'd leave the second term unchanged, then you'd leave the first term unchanged, and you'd take the derivative with respect to the second term. Okay, so that's all I'm doing up here is applying that chain rule. Now using our previously defined variables here, that means this first term here is y prime prime, and everything else I'll just leave as is. Now, if you have a look at both of these terms on the right-hand side, they look exactly like the two terms on the right-hand side of my equation 2 right here. Now, they might be in different orders, right? The y prime here is in the back, here the y prime is in the front, but it's the exact same expression. So that's kind of nice that this whole right-hand side means I can replace it by this simple derivative of one term involving multiplying two functions. So they are the exact same terms that appear there. So that means you can write now the full derivative with respect to x, just substitute inside, right? It has to be equal to this term, right? So we've gone from two terms down to one. Now what we do is just bring this to the other side, okay? And then that has to be equal to 0 if I do that. And the last thing I can do here is you notice here I have the derivative with respect to x is for both terms. So you can factor that out. All right, if I factor it out from the first term and from the second term, that means that I'm left with taking the derivative with respect to x of this complicated looking function, but it's going to be necessary to solve our problem. All right, so this is the last step. So if I have the derivative of some complicated function with respect to x that equals to 0, guess what? It means that whatever is in this square bracket right here must be equal to a constant value. Okay? If it's equal to a constant value, then you're going to satisfy this second equation. So it's this second equation here that we're going to use in order to use the Euler-Lagrange equation method to prove Snell's law for this problem. All right, so now let's go finish off this problem. All right, so we start with our equation here, f minus y prime df over dy prime must be equal to a constant value. And our function of f was defined earlier as our Lagrangian right here. First thing we can do is let's evaluate this second term right here. The second term is df over dy prime. The dy prime appears just under the square root term. So we can evaluate that derivative in a pretty straightforward manner here. Simply equals to this. All the other terms just remain constant. So the 1 over Vy remains, and you're left with this derivative here. Now what we can do is you could simplify that. You can cross out the 2's and just rewrite things a little bit more neatly as this expression right here. Okay, so now we have the second term in our star equation. So we're going to go ahead now and substitute both expressions over here and equals to a constant. So this is what it looks like. So you substitute f for the first term minus y prime multiplied by the second term is the derivative of f with respect to y prime. Okay, we haven't done anything too complicated. The next step now is maybe put things on a common denominator. Okay, so you can introduce a square root of 1 plus y prime squared over on the first term here. If you put things on a common denominator, things start to simplify nicely. I like it. We're moving in the right direction. Now you can see here you have the difference between the same two terms, so simply cancel those out. And at the end you can write this as a nice expression. That's it. Just replace that with the number 1. So you've done all of this work to show that 1 divided by the speed divided by the square root of 1 plus y prime squared must be equal to a constant. All right, so we're not quite at Snell's law. It doesn't look like Snell's law to me. We have one more step to do in order to prove Snell's law for this problem. All right, so you remember our definition now for y prime. Remember how we had defined y prime. We defined it first when we were looking at our small segment right here. All right, I'm just going to put a dashed line here, and what I'm going to do is I'm going to define the angle theta with respect to that vertical line right here. Okay, so we substitute in the y prime. We go back to our original definition of dy over dx. Okay, the next step I could do now is simply rewrite that, right? I can put things on a common denominator again. So that becomes square root of dx squared plus dy squared over dx squared. Now what you can do now is factor out a dx from this denominator and bring it all the way to the top. Okay, so that's what we can do for the next step. And then we can use the fact that we had a definition earlier, right? We had a definition for this square root of dx squared plus dy squared. That is exactly how we had defined the length element ds. Okay, so our very complicated expression here reduces to something that's pretty straightforward. Okay, the next thing we're going to do now is we're going to introduce that angle theta. Okay, if you look at that diagram over here, this diagram over here, you can see that the angle theta, if you use some trigonometry, should be able to write that sine of the angle theta is opposite over the hypotenuse. The opposite is dx over the hypotenuse ds. So that means you can simplify this in our expression here, and we can write as sine theta divided by the speed. Has to be equal to a constant. All right, we're almost there. The last step to do is remember the speed in any particular media with an index of refraction n. You can write that the speed is the speed of light in a vacuum, which is the letter c, divided by that index of refraction. So you go ahead now, you substitute that down here in the bottom. So you get our expression now is n sine theta divided by the speed of light equals to a constant. Well, guess what? The speed of light is a constant, right? This c is another constant. So all you do is you group it with the constant on the right-hand side, right? And you group those together, and they're just simply equal to another constant. So then we're left with Snell's law right here. And Snell's law says that the index of refraction multiplied by sine of the angle theta has to be equal to some constant value. All right, so that is a very complicated method of showing Snell's law using Euler-Lagrange equation. But Euler-Lagrange is a powerful method that allows you to solve very complex problems. All right, that's it for me, folks. Thanks for watching.